edges, and we may have just found proof that they actually exist. I'm Alex McColgan, and you're watching Astrum. Join with me as we delve into the darkness to solve the mysteries of primordial black holes. What are they? Where do they come from? And should we be worried? For a long time, tiny black holes, what I'm going to call black hole rhinos, seeing as they could have around the same mass, were thought to be impossible. Until the 1960s, we knew of exactly one way to make a black hole, and that was through stellar collapse. A star 20 times the mass of our Sun or greater, running out of fuel and exploding in a supernova. All that exploded matter collapses, leaving behind an object so dense, not even light could escape from its crushing gravity. This is a black hole. And because it formed from a star, it's a stellar black hole. But this isn't how all stars end. If their mass is less than 20 times that of the Sun, it still goes supernova, but the collapse isn't quite powerful enough to create a black hole. Instead, we see a neutron star, a tiny celestial object that's still incredibly dense and made up almost entirely of neutrons. And for stars smaller than 8 stellar masses, they don't go supernova at all. So there is a limit to how big stellar black holes can be at birth. No larger than the largest stars, maybe a few hundred times the mass of our Sun, and no smaller than a few times more massive. So why do we think that smaller than possible black holes could actually exist? Strangely, the answer is that we discovered bigger than possible ones. Today we know that at the heart of almost every large galaxy lies a gargantuan monster, a supermassive black hole. Back in the 60s, we were just beginning to discover these enormous beasts. The first quasar, a highly luminous and redshifted galactic center, was found in 1963, kickstarting a roughly decade-long golden age of black hole research. The first predictions of a massive black hole at the center of a galaxy came in 1971. As the years passed and more evidence of these titans came to light, we realized they were mind-bogglingly massive, hundreds of thousands to billions of times the mass of our Sun. But they are something of an enigma, and left scientists with one question in particular: how do they form? While it's technically possible that a stellar black hole could consume mass and eventually grow this big, this explanation started to break down as examples of supermassive black holes from earlier and earlier in the universe's history started showing up in our increasingly distant images of the cosmos. But for now at least, there wasn't a better explanation. Then came the James Webb Space Telescope. Launched on the 25th of December 2021 and switched on in 2022, it promised to see further and in better detail than any telescope had ever seen before. It would look for stars so distant, their light had started traveling at almost the dawn of the universe. And James Webb did not disappoint. These little red dots represent galaxies with supermassive black holes from just 500 million years after the Big Bang. Scientists realized this was not enough time for stellar black holes to grow to that size, not without devouring matter faster than the laws of physics should allow. Now, I've made a video on this idea before, and there is some evidence that this can happen, that black holes can disregard our speed limits on how fast they can eat to grow at rates we wouldn't initially have thought possible, that is, if we hadn't seen them doing it. But there are plenty of scientists who are skeptical of this answer, and there's an alternative theory, one that another recent James Webb discovery may have just confirmed as true. When it comes to forming a black hole, the key is density. When density is high enough, mass becomes so compact that its localized field of gravity passes a tipping point, and the speed at which you would have to move to get away from it becomes impossibly fast, i.e., you'd have to travel faster than the speed of light. Defying such gravity is impossible, but wouldn't it be fascinating if it wasn't? You'd be able to see the insane, physics-bending conditions that exist within the heart of a black hole and return to tell about it. While such a thing is beyond our reach, the sponsor of today's video, Novium, can bring a little bit of gravity defiance right to your own desk. Their hover pen Interstellar hangs there at a 23.5-degree angle in a nod to Earth's axial tilt, even as it brushes off its gravity. I've had this sleek, refillable pen on my desk for a while now, and I find it just as cool now as I did when I first got it. Made from aircraft-grade aluminium, it's a great gift for a space enthusiast, or for yourself if you're looking for a comfortable writing experience that also looks beautiful. And if you go for the premium version, it comes with a real shard of meteorite embedded in its tip, a piece of space that's older than the Earth itself. If you find that as cool as I do, check out the range of Novium hover pens such as the hover pen Interstellar or the hover pen Future by scanning my QR code or clicking the link in the description below. As a special Black Friday deal for the next 48 hours, if you use my code ASTROM at checkout, you'll get 20% off your purchase and free shipping worldwide. Now, back to black holes. As I mentioned, black holes are densely packed. The question is, how does matter get that dense in the first place? For that, you need a huge amount of energy, enough to overcome the electromagnetic force that stops electrons or protons from getting too close to each other. Then there's the neutron degeneracy pressure, a quantum mechanical force that says that two subatomic particles, two neutrons, can't occupy the same space at once. Neutron stars are not dense enough for their gravity to overcome this pressure, but they are still so dense that a spoonful of this matter would weigh as much as Mount Everest, over 900 billion kilograms. To make a black hole, you need forces able to crush the whole of Mount Everest into that teaspoon and then some. In fact, Mount Everest would have to be squashed into a space more than 1,000 times smaller than an atom to become a black hole. In the universe as it exists today, such forces only exist in very specific circumstances, inside collapsing stars as they turn supernova. But go back in time, and that wasn't always so. Let's rewind to the earliest moments of the universe, within the first second after the Big Bang. There, those pressures did exist, albeit just for a moment. In this hot, dense particle soup, the distribution of matter was not completely homogeneous or evenly distributed. There were areas of high particle density and others where it was lower. Scientists believe it's possible that in particularly dense patches of space, black holes could have formed from primordial matter itself, skipping the star phase entirely. The result is called primordial black holes, and surprisingly, they aren't actually a new idea. They were first predicted in 1966 by Yakov Zeldovich and Igor Novikov. What's interesting about them is that they could have formed with masses 100,000 times greater than that of our Sun. This would be more than enough to account for the supermassive black holes that we see today, especially given the billions of years they've had to grow. Curiously, they didn't have to form as giants. They could also have been much smaller. A black hole the size of a single atom, with mass comparable to an asteroid, or a so-called black hole rhino that would be no bigger than a proton, but the mass of a rhinoceros. However, this was 13.8 billion years ago, and there are two problems with the theory that such tiny black holes exist today. The first is Hawking radiation, an extremely long wavelength of radiation that Stephen Hawking hypothesized black holes emit, gradually shrinking them over vast timeframes. It essentially tells us that, by now, all tiny black holes should have evaporated away. The second problem is that we haven't proven that primordial black holes actually existed in the first place. We've never seen a black hole arise out of the interstellar dust, or at least we hadn't until recently. In July 2025, NASA reported that the James Webb Space Telescope had seen 2 early distant galaxies, likely in the process of crashing into each other. But strangely, between them, and not in the center of a galaxy of its own, was a supermassive black hole. It had not somehow been ejected from either galaxy. They also have their own supermassive black holes, which left this third one completely inexplicable. The team who found it proposed that the black hole formed in situ via the direct collapse of a gas cloud. But this isn't the only evidence that black holes can simply appear given the right conditions. QS01 is a supermassive black hole that was also spotted by Webb. It inhabits a surprisingly small galaxy. Scientists were able to do spectral analysis and found that it's incredibly low in heavy metals, elements other than hydrogen and helium. This galaxy had less than 1% of the oxygen that we see in our own, and researchers called it one of the most chemically unevolved systems found in the early universe, which is telling. Stars usually produce these elements in just their first few generations, so the fact that they are absent in QS01's galaxy suggests that very little stellar formation has taken place yet, compelling evidence that wherever QS01 had come from, it had likely not been birthed by a star. Now, although not smoking guns, these two examples lend weight to the idea that the early universe was capable of producing primordial black holes. In fact, this finding may explain where all supermassive black holes came from. And if that's true, then it's almost certain that super tiny black holes used to exist too. But they're all gone, right? By now they should have dissolved. Well, according to one theory, perhaps not. Astronomy has a problem on its hands. As we track the amount of gravitational pull in the universe, it is much higher than it should be. Scientists conclude that there is additional matter inside galaxies, or circling them in large halos, something they've dubbed dark matter, because we can't see it. But you know what else carries serious mass and is quite hard to see? Black holes. Particularly ones with no accretion disks, because they form directly out of interstellar matter. Of course, scientists have investigated this idea, and there's no evidence of large black holes surrounding the Milky Way. If there were, stars would go flying like bowling pins every time one fell into our galaxy. We'd also see the light from stars behind them behaving strangely through the power of gravitational lensing, as the intense gravity of these black holes distorts the space around them, and we simply don't see anything that matches up to this. But tiny black holes, our black hole rhinos, would be very hard to detect through either means. There's no proof they're not there. The only argument is to say that they would have all dissolved by now, but this might not be the case. In April 2024, a study published in the monthly notices of the Royal Astronomical Society found that at tiny levels, Hawking radiation might slow down considerably, almost stopping entirely, which means these black holes might shrink and shrink until they eventually stop, which, if true, means that black hole rhinos might be out there. Many believe dark matter circles our galaxy in a massive halo. What if, instead of all of that, it was tiny black hole rhinos? There could be millions and millions of them out there. A black hole minefield, lying invisible and deadly. A swarm we could someday encounter if we ever attempted to leave the galaxy to explore another. We might be caged here without knowing it. Of course, Space exploration has plenty of dangers all of its own, but it's more than unsettling to consider that as we voyage out into the dark, we could be on a collision course with a tiny, microscopic black hole with the mass of a rhino, or that one could be hurtling through space on its way towards us. Let's hope we find some evidence that this particular theory isn't true, or at least forget the idea of leaving the galaxy. I think I'd rather stay at home. Thanks for watching, and a special mention to Charlie Phillips. Thank you for supporting us as a Supernova tier member on Patreon. It means a lot. Astrum isn't just made possible with sponsors and ads, it thrives because of our Patreons. Please join us so we can keep creating more and better videos and making space accessible for everyone. Patreon is where viewers become part of what keeps Astrum running. We're building something steady and long-term, and every new member makes it stronger.
Dane, ăstea nu ne mai omor.
De ce?
Ne-am dat imortalitate.
Păi și cum îți dai?
Am eu ceva meniu special.
Ia stai că-mi vine o creatură. M-a omorât. Totuși. M-a omorât. Eu odie. Văd acum ceva. Mamă, deja văd cum stă. Mamă, iarăși m-am trezit. Bă, frate, ce faceți?
Eu îl dau revive cu meniul ăla.
Păi eu am făcut de 3 ori. De 3 ori. Păi a 3-a oră.
Gata, acum nu se mai pune, că avem viteză mare. Nu, am activat ceva admin panel. Ankle breaker trainee. Bă, pe mine ăsta mă omoară. Bă, nu mă omoară. Ăștia sunt prietenoși acum. Ce? La cum ai văzut că fugeam?
E mult. Păi de ce?
Oh, stai.
Niciodată o prietenos, nu merg aia.
Mamă,
Hai bine.
bă, Jean, la astea le e frică de mine.
Bă, dar ăla m-a omorât. Vulpița aia. Vulpița aia m-a omorât.
Gata. Vă dau respawn la amândoi.
În parte nu. În parte nu, că aparte toate potimele. Pe toate jocurile?
Nu, că eu nu sunt hacker.
Uite, scrie pe chat.
Ai ceva buton cu capul lui Freddy.
E mulți, poate ne mai ca lui Betty.
Nu.
Bine, sunt omul.
Eu nu te pune n-ai făcut. Ranu, nu vezi capul lui Freddy pe acolo?
Da?
Uite, vezi, gata.
Și le vezi pe toate?
Nu.
Păi eu nu. Le-am început. Le-am început. Bă, stai că pun toate creaturile. Da, și ce fac eu, eu le șterg. Le-am șterg, să știți. Haideți să facem.
Nu suntem picot. Iau-mi toate chestiile eu.
Haide, Remus, să știi că nu mai ai nicio creatură că am șters. Uite, vezi?
Ia uite-te.
Vezi? Eu le-am șters. Vezi? Le-am șters. Nu poți să le ștergi, nu?
Nu poți să le ștergi.
Ba, da, am făcut. Uite, caută peste tot.
Ia mă, tu uite cum te mănâncă adevăr. Ia mă, te depărta mine tu capul meu. Ia mă, tu mă-nducă. Nu. Ia mă, ia mine nu tu-mi vii.
Tu faci unde? Remus,
E Freddy la ușă.
ce ziceți vă să ne jucăm niște note, nu? Vreți? Vreți, mă, nu știu. Am săturat puțin de cu ăsta plictisitor.
Nu e plictisitor, bă, ți-am dat viteză infinită. Nu ne dai în bine viață să ne spună. Băi, eu te-am dat. Stai, tu ai capul lui Freddy? Ia dă-mi, ia arată-mi. Da, lai. Adică... E fauna tăită. Eu nu te-am murit. E mutat pe mine cu el? Dacă puteți opine pe baza asta.
Vamos de când.
Dengi.
Emu, bă, dar haideți bă să ne jucăm cu cineva un joc interesant. Auzi? Auzi, vezi că tu la grup adrese tot. Ai, ok?